Alrighty, thanks Janice. Okay, so yeah, my name's Zach Clark and I'm a postdoc at Macquarie Uni. And today I was just going to talk a little bit about some of the work that formed part of my PhD, looking at how dryland rivers respond to climate change over a range of different scales, both in the past, over the last few thousand years, and potentially into the future, into coming decades. So dryland rivers are critically important systems in Australia and around the world, but they're quite often poorly understood. And it's particularly unclear how sensitive dryland rivers are to changing catchment conditions brought about by climate change, for example. And this is largely due to the inherent variability of dryland rivers in terms of their hydrology and their geomorphology. But given the overarching influence of river geomorphology on ecosystem structure and functioning, on land use, on cultural and recreational uses of dryland rivers, it's particularly important that we understand how these rivers might respond to future climate change. So by understanding the long-term evolution of a system, we can contextualize the modern systems to some degree, and we can start to define thresholds of change in certain systems, and we can also improve our understanding of potential future pathways of change in some of these dryland rivers. So as I said, today I'm going to talk a little bit about some of the work that formed part of my PhD, and two key questions that guided my research were focused on understanding how dryland rivers have responded to climate-driven hydrological change in the past, and how dryland rivers might respond into the future. So today I'm going to talk about a couple of Australian rivers that have responded quite dramatically to Holocene climatic changes over the last few thousand years, the Warrego and the Macquarie rivers in particular. And then I'm going to look at the sort of diversity of present-day Australian rivers before looking at how they might respond to future climate change over coming decades. So the Warrego River is in the northern Murray-Darling Basin. It flows south from headwater catchments in the Carnarvon Ranges of central Queensland. In its middle to lower reaches, it flows across a large sort of low-angled alluvial fan that's traversed by a number of distributary channels that all inevitably disintegrate into ephemeral wetlands at their lower ends. The Warrego itself sort of flows ephemerally, intermittently, and it persists for much of the time as a string of disconnected waterholes with dry channels along most of its length. But it's also characterised by occasional very large floods, often associated with the La Nina phase of the Southern Oscillation. These floods can inundate up to 3,000 square kilometres of riverine and floodplain wetlands in the Warrego. So it has a classic sort of boom and bust hydrology that we see in dryland rivers across Australia. And this is a Google Earth screenshot of the Warrego fan. And the panel on the right is, I've zoomed in on a section of the Warrego near Cunnamulla in southwest Queensland. And on the left is the modern Warrego, which is relatively small. It's quite straight with a number of anabranching channels. But just to the east, we can see a number of quite large meandering paleo channels preserved on the floodplain surface. So a few years ago, we targeted these paleo channels for luminescence dating to establish when they were active. And this sediment dating suggests that these channels were actively migrating across the floodplain between about 8,000 to 4,500 years ago. These channels were substantially larger than the modern river today, up to about 160 metres in width, transporting 20 to 30 times as much water as the modern river does today on average. And the meandering plan form of these channels suggests that flow is much more regular than it is today, and much higher energy to allow the Warrego to maintain an actively migrating meandering channel in this sort of very low gradient landscape. Then after 4,500 years ago, there was a sort of step change in the character of the Warrego River to come to resemble the modern system, which is, as I said, much smaller, much lower energy with straight and anabranching channels. And as I said, it persists for much of the time as a sort of string of isolated water holes. And this quite dramatic change in the character of the Warrego was brought about by catchment aridification. And the Holocene climate drivers responsible for this, which I'll go into in a little bit, were relatively modest compared to other periods of climate change in the late Quaternary. So it suggests that the Warrego was somewhat near a threshold of change that made it quite sensitive to the hydroclimatic changes that we saw in the Holocene. And this period of enhanced flow in the mid-Holocene and subsequent drying out in the late Holocene over the last few thousand years is a pattern that we've seen in a number of dryland rivers across Australia and overseas as well. And one of the other more well-documented rivers where we see this is also in the northern Murray-Darling Basin. It's the Macquarie River. So the Macquarie has a similar pattern and timing of change to the Warrego. During the mid-Holocene, the Macquarie was a very large meandering channel, about 18 times the size of the modern system, and it maintained a continuous course to the Barwon River at its downstream end. Then again, after about 5,000 years ago, the Macquarie underwent sort of a dramatic shift in its character and its behaviour to come to resemble the modern system, which declines dramatically in size and discharge downstream, and eventually breaks down into the complex system of anabranching channels and extensive wetlands that are known as the Macquarie Marshes today. So I'll quickly go into the hydroclimatic drivers responsible for this, just to preempt any sort of questions about that. So during the early to mid-Holocene, the Pacific Ocean was in a relatively persistent La Nina phase of the El Nino Southern Oscillation. And this increased summer rainfall over eastern and northern Australia. And there was much less variability in the Southern Oscillation than we see today. Then after about 5,000 years ago, an increased frequency of El Nino events increased climatic variability across eastern and northern Australia, and effectively increased aridity across eastern Australia and the dryland catchments there. So we've seen that mid to late Holocene climate change triggered quite dramatic responses in the character and the behaviour of both the Warrego and the Macquarie rivers. And given that future projected changes to climate are in some ways similar to what we've seen in the mid to late Holocene, in that we're expecting reduction in rainfall, reduction in stream flow, and increasing climatic variability, it begs the question, how might Australian dryland rivers respond to this changing climate into the future? So to address this, we have to look at the diversity of present-day Australian rivers and then look at the specific changes in climate that we can expect in some of these catchments. So firstly, I started by categorising Australian dryland rivers into 5 different types based on their geomorphology. So from sort of what I've called type 1 rivers, these are through-going rivers that maintain channel size and discharge downstream. These are generally found in the more well-watered catchments down in Victoria, in the southeastern highlands, but they nonetheless flow through dryland areas in their lower reaches. Then type 2 rivers, these are rivers that decline in size downstream but maintain a continuous channelized course. So an example here would be the Murrumbidgee River in southern New South Wales. Type 3 rivers, these are sinuous rivers, but they decline dramatically in size downstream and are ultimately characterised by channel breakdown and extensive formation of wetlands on the floodplain. An example here would be the Macquarie River and the modern Macquarie Marshes. Type 4 rivers, these sort of resemble the modern Warrego. So these are very low energy, they're straight rivers, and they break down to form ephemeral wetlands on the floodplain. Lastly, type 5 rivers, these terminate in floodouts and are generally not associated with wetlands, and these are typically clustered in central Australia. So statistical analysis confirms that these 5 river types are significantly different from one another based on a range of geomorphological, hydrological and climatic variables. And this panel on the right sort of visualises the differences and the similarities between these different river types. So the closer rivers are together on this figure, the more similar they are based on their geomorphology, hydrology and climate. And you can see the river types that I just explained fall out, cluster fairly well. But interestingly, the variable that best differentiates river types, except for types 4 and 5, the variable that best differentiates these river types is mean catchment aridity, which is essentially the ratio of rainfall to potential evapotranspiration. So it's a rough sort of measurement of water balance in the catchment. So this allows us to define thresholds of aridity between these different river types. So now if we project forward and model aridity across Australia into the future, we can look at whether or not certain rivers are likely to cross these aridity thresholds into the future. So with using a range of global climate model outputs, I've modelled aridity across the Australian continent out to 2070. And under a relatively moderate scenario, the arid zone, which is this light grey area here, is expected to expand quite considerably, well into the western half of the Murray-Darling Basin here, and almost entirely swallowing the Lake Eyre Basin. But perhaps more importantly, the humid fringe around the coastline and around the Great Dividing Range, particularly where a lot of Murray-Darling Basin rivers have their headwater catchments, these humid areas are expected to shrink and contract quite significantly. So by defining aridity thresholds between different river types and by projecting future aridity for each of these dryland catchments, I've estimated that many Australian dryland rivers, I think about 23 of the 29 that I looked at, are expected to cross one of these aridity thresholds by 2070 and are therefore potentially likely to undergo some sort of geomorphological change as a result of this catchment aridification. And these changes are likely to occur in the form of sort of increased likelihood of river discontinuity, flow disconnection and channel breakdown. And changes to river structure of this sort of magnitude would have considerable flow-on effects for ecosystem dynamics, for wetland inundation frequencies, and for the ecosystem services that these rivers provide in what are already marginal landscapes. So sort of to summarise quickly, we've seen that some dryland rivers have been quite sensitive to climatic changes that we've seen over the last few thousand years, and many Australian dryland rivers may be sensitive to the types of change that we're expecting to see over the next 50 or so years. There are, of course, a lot of uncertainties around this, particularly related to human activities and water resource management, but also related to lags in some of these systems between climatic changes, which can occur quite quickly, and the geomorphic changes, which might lag that significantly. So understanding how these quite complicated systems will respond to future climate change requires a lot of ongoing research and is a particularly important research challenge moving forward, I think. And I'll leave it there for the moment.